Now I would like to welcome Ric Derbyshire, a security researcher, principal security researcher at Orange Cyber Defense, and also an honorary researcher at the Imperial College of London. He has a PhD and he researches mostly a pragmatic approach to both offensive and defensive elements of cybersecurity with a focus on operational technology. That's where he's definitely very different than the rest of the speakers today. There is a focus on OT, on PLCs, and that's also what his presentation will be about. Dead man's programmable logic controller and how ransomware operations are abusing it. Please welcome Ric on stage. Ric, you have the floor. Thank you very much.
Thank you very much for such a wonderful introduction. And thank you to the Centre for Cybersecurity Belgium for allowing me to be here. And thank you everybody for being here as well to see this. My name is Ric. As described, I'm a principal security researcher at Orange Cyber Defense. And rather than kind of looking at what's currently happening or what has happened in terms of threat intelligence, today I want to take you a little bit into the future of what may happen with ransoming the physical world via operational technology. That's using a technique that we've called dead man's PLC, which will be more apparent as we go through. So I want to set the scene very briefly with the OT apocalypse that we're currently experiencing. We're seeing oil refineries shut down after cyber attacks on their industrial control systems. We're seeing factories having their robots disabled by cyber criminals, and we're seeing nation states plunged into darkness by cyber attacks, paralyzing their power grid. The eagle-eyed among you might realize that all of those were made up, and that's not really the case. We're seeing something quite a little bit different. At Orange, we've been collecting a data set for the past few years of cyber attacks that have actually impacted operational technology, and we've been very strict with the criteria on what we actually categorize here. What you're seeing on screen is a Sankey chart made up of some of the major bits of the data that we've collected. Moving from the left, what you can see from this elephant in the room, or on the slide, if you will, is this big bar across the top. Starting in around 2020, we've seen criminals using IT-specific tactics, techniques, and procedures to target IT and to hit level 5 of the Purdue model, which I'll explain very shortly. But somehow these IT attacks are affecting operational technology. It's very strange. The reason for that is the advent of ransomware as a service and double extortion, which came about in roughly 2020. And they're affecting operational technology for a couple of reasons. The main reason is that there may be dependencies within the IT that get ransomed that the OT cannot function without. The other reason is that the OT may be either disconnected or shut down due to either an abundance of caution or frankly, the distrust of security controls or the network architecture separating the OT from the IT. Now, there are a number of ways to skin the metaphorical cat that is cyber extortion or ransomware. And this is a non-comprehensive kill chain that we are looking at right now. And essentially, there are a number of ways to go through this technical procedure to essentially get to what is on the right of the slide, which are those 7 criteria to actually be able to perform a crime, or at least an extortion, which is a threat, a demand, a proof of life, a pressure, a way to facilitate negotiation, to receive a payment, and a way to return the extorted goods, data, or whatever. What's really interesting is when you look at that and you really consider that, none of the technical elements necessarily need be there. What's important is that crime element. And when we look at it as a crime, we can start looking at it through a criminological lens. One of those lenses could be routine activity theory, which is a criminological theory with 3 specific pillars. There must be a likely offender, so someone that is actually willing to do the crime and motivated to do the crime with a viable modus operandi. There needs to be a suitable target, so a vulnerable victim, and suitable time for the criminal to actually perpetrate their crime. And there needs to be an absence of a capable guardian. In typical crime, physical crime, this would just be a lack of law enforcement. But in terms of cybercrime, that can also be either a lack or an ineffectiveness of cybersecurity controls. If we bring this all back to operational technology, we can see that there are two of those pillars definitely there for a crime to take place. The first is a suitable target. Operational technology is no less vulnerable, in fact, maybe more vulnerable than typical IT, which is already suffering from a ransomware epidemic. But there's also an absence of a capable guardian. We already know that despite today's exciting news with potentially Scattered Spider being arrested in the UK, law enforcement struggle to actually apprehend cyber criminals for a number of very understandable reasons. But also, it's very difficult to put into place particularly effective cybersecurity controls for operational technology, just due to the nature of those environments. However, what is missing from this part of routine activity theory is the likely offender. And while likely offenders would be willing and motivated to extort operational technology, what's really missing there is their viable modus operandi to monetize an attack on operational technology. Now, I want to give an OT context before we go any further and explain for those that might not be familiar with some OT things, just some terminology and things that we might be using later on, and maybe just a bit of a primer. The first thing are two very important devices we need to consider and kind of the main flavor that makes something operational technology. The first on the left-hand side is the programmable logic controller, which is essentially the heart of the operational process. What these do is they sense the environment around them via various types of sensors, and then they actuate the environment around them according to their configuration via things like pumps, valves, robots, conveyors, or any other thing like that. The other thing that we need to consider here is the human-machine interface, which provides operators with essentially situational awareness of what's happening in the process. This can either be in the form of a Windows PC with software on it, or as you can see on screen, hardware panels that may have touchscreens. These will typically show like a diagram of what's going on in the process that might even be animated that will show, for example, how much fluid is in a tank. And they may allow certain limited levels of actuation of the physical environment that the operator can do while they're actually there with the device. The next thing to consider is to step back and look at the operational process as a whole. And what we're looking at here is the Purdue Enterprise Reference Architecture, or more typically known as the Purdue model. Now, you'll hear people say that this is either useless or an actual architecture that you should implement your environments specifically towards. But it kind of is neither. And the main point is that it's a really useful communication device so that people are speaking with this familiar language to one another. So that when they say, oh, a certain level, or they say a certain device, they kind of have this understanding of this like spatial awareness. The three things I want to draw your eye to are the orange dashed lines, those boxes. The top one, containing levels 4 and 5, is the enterprise zone. And this is the typical IT infrastructure that you're probably familiar with in most organizations. The bottom one is the operational technology. As we go down, what we can see is we get progressively closer to the physical environment. So we start off with the top at level 3 with things like engineering workstations that configure and push code to the programmable logic controllers, historians that collect telemetry. We might see SCADA and things like that as well. And as we move closer down, we get to level 0, which are actually the sensors and actuators that may be those pumps and valves that we've been talking about. In between those two that I've just discussed, we have level 3.5, which is the demilitarized zone, which is slowly becoming more and more diminished as we have this IT-OT convergence. And the intent of this is to essentially act as a separation layer between the ever-growing attack surface of the IT and enterprise zone and the very vulnerable operational technology below it that we find difficult to actually defend other than have a strong perimeter. When we were creating the data set that I showed you earlier on in terms of that Sankey chart, to understand it a little bit better, and you might have noticed these categories already, we created the small taxonomy to kind of basically categorized the data in a way that helped us understand it. This wasn't necessarily something that we wanted to publish and run with originally. It was something just for us internally, but it's been really quite useful for us to explain things to people. So the categories, the high level categories 1 and 2 at the top. So level 1, or sorry, category 1 is those attacks that exclusively use IT tactics, techniques, and procedures. And category 2 are those that include the use of OT tactics, techniques, and procedures. These then get split further down. So category 1 gets split into 1A, B, and C, with 1A being specifically targeted at IT, 1B specifically being targeted at IT and OT. This could be either an opportunistic or an accidental spillover into the OT. And then 1C is a specific IT attack targeted at the operational technology, because while we do have programmable logic controllers and human machine interfaces that are kind of embedded devices, we also do have lots of commercial off-the-shelf operating systems like Linux and Windows as well. Category 2, those that include the use of operational technology, tactics, techniques, and procedures, obviously are going to target operational technology. So we can't delineate that by whether it's split into IT or OT targeting. Instead, we can actually look at distinct differences between targeting that is crude and targeting that is sophisticated. Here, a crude attack may be something like a basic denial of service and knocking a PLC over, or it might be something like brute forcing a human machine interface authentication. However, a sophisticated attack would be something where the adversary really tries to consider the physical process and understand how it works, how best to achieve a specific and meaningful impact that they want to achieve, and then how they can actually achieve that by doing a tactic that's unique to operational technology attacks called process comprehension. What we currently see with these ransomware attacks is that they're very much specifically type 1A attacks, which we saw at the diagram very early on. With Deadman's PLC, what we wanted to do was shift it all the way to the other end to type 2B, the sophisticated OT targeted attack. To be able to do this, we identified a few criteria that we needed to achieve to be able to actually bring this to fruition. The first is it has to be scalable. One big problem with ransomware as a defender is that it's so pervasive. It's everywhere, and it's very easy for low-skilled attackers to be able to essentially take something that is existing, like a methodology that already exists, and then just put it, just use it themselves and start attacking people with it. We needed to be able to translate that kind of scalability to operational technology. And traditional attempts to do things like encrypt a PLC just fall flat, because to encrypt a PLC, you need some sort of remote code execution vulnerability. But that very quickly becomes unscalable because PLCs have different models, different firmware versions, and different vendor ecosystems that all require different remote code execution vulnerabilities to be exploited, which immediately makes it very costly to do. So we had to do something that was achievable by just accessing the OT environment. It also has to be stable. While typical IT ransomware can just immediately cause some sort of chaos, with an OT environment, if we immediately just impact them, then they're not going to focus on paying a ransom. They're going to focus on recovery. So while we want to be able to cause a credible threat, which is our next criterion, we actually need it to remain stable for the for essentially the threat of something happening being more of the incentive to pay rather than something actually happening. Leading on to that, if we're going to threaten something, the threat has to be credible and it has to be really optimized. So we have to be able to be in a position to really understand how we can impact the operational process in some meaningful way. We also have to be able to detect tampering and prevent recovery, the next two criteria. Those mean that our attack, while remaining stable, has to also prevent the victim from being able to stop and get involved and try and stop us from doing it. That means that they can't tamper with the attack, and they also can't recover from the attack. And then finally, we have to be able to disarm on payment, because while we are criminals, we have to be honorable criminals, right? Because if we scam one victim, the next victim will know that we've scammed the first and they won't be incentivized to pay. So we have to be able to release the OT environment back to the victim once that they've paid. So that's how we get to Deadman's PLC. So if we go back very quickly to the cyber extortion kill chain, we want to be able to compare that to the Deadman's PLC kill chain, if you will. And what you can see here is we can follow very much a similar process and always end up at those 7 criteria of a crime. I first want to tell you about how it works. And we're going to run through a very quick implementation, both through diagrams and also through screenshots of an implementation itself. And then I want to tell you about why it works through animations and also through some videos of some demo of it working. So the more focused of you might have noticed that we used the same diagram for the kill chain, but switched a few things around. Those are the intrusion, positioning, and threat model, the internal reconnaissance and preparing dead man's PLC, and then finally deploying and arming dead man's PLC. And those are the sections that we're going to focus on now. The first and quickest is the intrusion, positioning, and threat model. To be able to do dead man's PLC as an attack, we need to be able to land on the engineering workstation, which is typically going to be a Windows PC that has some software on it that can then configure the PLCs in the environment. While that sounds like we're already starting at a very deep place, a recent SANS report, or fairly recent SANS report, noted that over 34% of attacks impacting operational technology did actually manage to access the engineering workstation. So this isn't in an unfeasible realm. That might mean that we have to go through the internet, enterprise network, demilitarized zone, and hit the engineering workstation, or it could be an increasingly realistic thing where we actually get access through some unsecured remote access that is within the OT already. So let's assume that we've got access to our engineering workstation, and there it is right there. The first thing we want to do is be able to identify and validate the current PLC project that's on that. This is the PLC project file that is essentially controlling and configuring the PLCs. This may look a little bit like this, and this screenshot is cropped from Siemens TIA portal, and we're using Siemens for the rest of this talk because it's the vendor with the biggest market share, but any vendor ecosystem is vulnerable to this. So now what we can see is that we can see a few PLCs that have green ticks. We can see an S7 300, 1200, and 1500 in roughly the top third of the screenshot. Those green ticks mean that that this configuration software knows that this project file is currently live and running on the PLCs, and this code is currently running. So what we do now with our diagram is we know that the PLCs exist. We know which ones we have access to, and we know the code that is running on them. The next step is to identify pre-existing PLC to PLC relationships, and this gets important later on because we're going to build on this and extend it. Again, in our software that we're looking at and have access to, it might look a little bit like this, where we know which PLCs are talking to one another and which we can talk to as well. So on our diagram, which doesn't match the screenshot that I've just shown you because it's for illustrative purposes, it might look a little bit like this, where we say, okay, these PLCs are talking to one another right now, so we know which ones we can build on and which ones we have to build ourselves. The next thing that we need to do is identify core code blocks. And in our demo, it looks like this, and it might look a little bit like this, but far more complex in a live environment. The reason for doing this is twofold. The first is that we need to keep the environment stable. So while we haven't enacted the consequences, we need to know that whatever we've implemented doesn't interfere with this. However, also knowing about this core code block and starting to study it means that we understand the actual physical environment and how it's being interacted with the operational technology a lot more. And so that means we can optimize our consequences if we need to enact them. So that means that now we know how not to interfere with the PLCs that are currently using the legitimate code, but should the time arise, we know how to best destroy them as well. That's our preparation done, and we need to deploy an armed dead man's PLC next. The first thing we need to do is introduce a covert monitoring network. So we're going to take away the diagram there, and we're going to start building our own. So the first thing that we need to do is we need to enact a heartbeat network. And what this means is that each PLC will, or even asset under our control, will talk to one another. What this means is that a device will send a heartbeat to another device. And that happens for every asset under our control. That'll become more apparent in a moment. What this does is this means that if a device sending a heartbeat cannot send it, the device receiving it must have been tampered with. And if the device receiving a heartbeat does not receive one, it means the device sending one has been tampered with. So what this does is this acts as a dead man's switch between every asset under our control, which is where the name dead man's PLC comes from. This is done by adding some code to the PLC logic, but also for the engineering workstation that's also under our control. For the Siemens ecosystem, we can use the Python library Snap7. Although this heartbeat network is extremely effective already, it's only for local devices talking to one another. We also need to introduce an alerting network, which means that if a device notices that there has been some tampering, it can also then propagate out an alert to the entire network of assets under our control, which means that if there is a single tampering anywhere in the network that we control, it propagates out everywhere so that we are completely situationally aware to any tampering and are ready to enact any tampering anywhere. Sorry, any consequences anywhere. So we've built in our heartbeats and everything is talking to one another. And we've also built in our alerting network. The next thing to do is prevent the introduction of recovery devices, because although someone may try and recover from the engineering workstation, it's also possible that an engineer may take a programming laptop and plug it into a network port of a programmable logic controller. The way of dealing with this is essentially when we push the code to the PLCs, we take a baseline of the connections that currently exist. And if the connections drop or increase, we enact the consequences. So that means, for example, if an engineer tries to introduce a laptop or a programming device of any sort, we're waiting for it, we propagate out an alert, and we enact the consequences. We're keeping the environment stable right now, which means that no adverse effects have happened for the victim, which means they're not incentivized to pay until we introduce a time limit. This is possibly the most simple part, where we just introduce a time limit through some PLC logic and also on the engineering workstation. This might be a day, a week, or whatever. This is simple, and it would just basically present some sort of time frame that they have to pay within, and if it gets to 0, the consequences are enacted. We also need to implement the most crucial part, which is the code that disrupts the process. The first part of this is that we need to interrupt the current legitimate code. We need to cease any existing code happening such that the actual physical process doesn't continue to work. We then, through our knowledge of the current existing code that's running, can optimize an attack to make sure that we cause the most damage possible on the physical environment. In our demo, it's really simple. You'll see we call it conveyor.exe rather than the traditional itcalc.exe. We do some really simple things of just turning some zeros to ones and ones to zeros, or sets to resets and resets to sets, as they're actually known in the Siemens ecosystem. But we'll show that shortly. So what that means is that if there is some sort of time limit ending or some sort of tampering or attempt at recovery, the heartbeats stop, the alerts propagate out, and the consequences are enacted. We also need to prevent the victim from reversing changes. For example, what happens if all of our current tamper-resistant processes fail for some reason? This is possibly the cheekiest and most interesting part. There are functionality throughout most operational technology to password protect project files with encryption, to password protect PLCs so that they can't be accessed without authentication, and all sorts of things like that. Typically, though, fortunately for us, they're not used, but we have lots of access to them ourselves. So what we can do is simply encrypt the project file once we're done with it with a password, and also password protect all the PLCs. So at least someone's getting use of that functionality, which means everything is nicely password protected just for our sake, which means that even if they do want to try and tamper with or prevent recovery or recover or anything like that, they have to get through the password protection from that as well. The last thing to do is arm dead man's PLC. So what we're going to do is take away all of the heartbeats and alerts because they actually don't exist yet because we've just built the configuration. We still need to push that. But it's also very crucial that we have an arming procedure, because if we just push dead man's PLC out and the code started functioning immediately, that might not land on the PLCs all at the same time. That might cause instability and an unfortunate premature enactment of the consequences, which means we have to have a very simple arming process. So the last thing to do for us is push the code to the existing code that is modified with dead man's PLC, and then arm it such that the heartbeat system and the alerting system begins to work. The last thing to do then is our extortion, or crime, the threat, demand, proof of life pressure, negotiation, payment, and eventual return as long as we've been paid. So let's talk a little bit about why that works. The first thing is the heartbeats in the alert system. Essentially, everything is talking to one another. Both the heartbeats are happening and also the alerting is checking on one another constantly, because the alert bit that may be on one PLC might set, but we don't know about that unless we're constantly checking on it. So this both needs to check on one another to be a dead man switch and then propagate out with the alert system. The way this looks a little bit like this. What we're looking at on screen at the moment is essentially the main thing, which is TIA portal, and we're looking at a VAT or watch table, and we can see lots of little false tags with little green or grey boxes that will flash depending on the variables that we've set for things like alerts and heartbeats. And then the command prompt that you can see is a very rudimentary proof of concept work of our actual Deadman's PLC control system. What we're going to do is we're going to arm Deadman's PLC. It's going to come up with a payment system, payment option, which we're not going to use right now. We're going to minimize that. And what you can see in the watch table is that the heartbeats are starting to talk to one another, which means the PLCs are talking to one another. And we can see the readout for that and that the alerts are still 0 in the command prompt. Cool. So now what happens if any of those heartbeats are interrupted, or, for example, the alert system propagates out? That might happen by one of our PLCs, such as PLC 3 being removed. That means the heartbeats stop, the alerts propagate out, and we enact the consequences. To demonstrate that, we're going to have a look at conveyor.exe, which is in a piece of software that virtualizes physical environments called Factory IO. What we can see here is essentially two very simple processes: a conveyor that brings boxes on, and a conveyor that brings boxes off, and a nice little robot that moves the boxes between the conveyor belts. We've enabled or armed Deadman's PLC again, and we don't need that pesky payment window, so we're going to minimize it one more time. And we're going to look at the alert system, the heartbeat systems, which are working fine. If we go over to conveyor.exe one more time very quickly, we can actually see that the whole system, conveyor.exe, is still stable, which is one of our criteria. However, what happens if PLC 3, like in the animation, gets removed? Well, we can do that right now. We can remove it. That's not my hands. This is a video, by the way. And we can see that the heartbeats are interrupted and the alerts propagate out. We can see that happening through the watch tables. And then finally, if we look over to conveyor.exe, oh no, there's a big mess. There's boxes everywhere. That's terrible. So great. We can move over now to the next video. There's a time limit here, right? Because if they don't pay in time, that's a big problem as well for them specifically. So we can't leave it stable forever. So for this animation, I left a very painful 10-second timer for the animation. But yeah, the timer ran out, the heartbeat stopped, the alerts propagated, and the consequences were enacted. This looks a little bit like this. We go back again to conveyor.exe, and everything is running happily again. The two conveyors are working fine, and the lovely little robot is having a great time moving boxes. But we've armed Deadman's PLC, and we're going to get rid of that nasty payment window now. I left a crucial 10-second window here as well. So while we can see very quickly that the conveyor.exe is stable, we've now run out of time. So if we then look back over to conveyor.exe, unfortunately, everything has gone wrong again for the victim. They should have paid. And for our final scenario, we want to look at what happens if the victim does pay their ransom. So we're there asking for our money. They pay for it. The nice little sign goes green. A nice little happy smiley face happens. We stop the heartbeats. We stop the alerts, and no consequences are enacted. The environment is released. For a last visit to conveyor.exe, we can see again everything is running happy. What we're going to do is then arm Deadman's PLC. But this time we're not going to get rid of the payment window. We're going to leave it there. But just quickly, we're going to make sure that everything is still stable just for this proof of concept, because we need to be rigorous here. Everything is still stable in conveyor.exe land. But the victims this time have decided that they need to pay. It's too important for their process to be interrupted or worse, destroyed. So they put in the super secret command of 1234. Here, Deadman's PLC is cancelled and conveyor.exe lives to move boxes another day. Cool. This would be a really bad talk if I didn't talk about defenses. The first thing are the three kind of defenses that you could do while you're actually, you haven't had Deadman's PLC deployed on your network. I want very crucially to talk about the network defenses first. The thing to do here is to really focus on that perimeter. And this is a tired trope for operational technology. And unfortunately, we're seeing this perimeter be slowly eroded by lots of requirements for functionality, both into and out of the operational technology environment. But there are ways by specifically focusing on how you control the inputs and outputs to that environment, and also using things like data diodes that you can actually really carefully control how the OT environment is accessed. For the engineering workstation, there are other things you can do. You can keep the engineering workstation shut down or completely logged out until the time when it's actually required. You can keep it up to date because typically these are going to be Windows devices. But there's an interesting one as well here where in a lot of cases, for a lot of vendors, the license key to actually turn the engineering workstation software on is on a USB stick, which can act as a physical second layer of authentication. So you can essentially bake in multi-factor authentication to the license key and keep the engineering workstation from being able to even load up the software to begin with without that multi-factor authentication. And finally, for programmable logic controllers, there isn't much you can do. But one of the things that we take advantage of to prevent recovery is password protection. So essentially, any password here is better than no password. And it doesn't matter if the password is the same throughout all of the programmable logic controllers, because it can act as at least some line of defense before you find that there's an adversary in your environment through some other mechanism like network detection, for example. But what happens if you want to defend after Deadman's PLC has been deployed? Unfortunately, there's not much you can do, and we've red teamed this all over the world with different people, and there isn't really anything you can do other than a graceless shutdown of your environment, which is typically going to be as much time offline as if you hadn't paid the ransom, if not more. Finally, I want to conclude with a few takeaways. The first is that attacks that impact OT environments are increasing, but they're only a surge of attacks against IT environments through cyber extortion and ransomware. A viable modus operandi is all cyber criminals need to move to operational technology. They just need to monetize it. And that's possible all while living off the land without any 0 days or any exploits at all with the use of a technique like Deadman's PLC. And finally, good or best practice would prevent something like Deadman's PLC deploying, but not much can be done once it is deployed and it is armed. Thank you very much. I've been Rick. If you want to read the paper that we published for Deadman's PLC, that's available in Digital Threats Research and Practice, which is a top QR code. If you want to look at our data set and the visualizations that we've done there, check out our annual report, The Security Navigator. Check out page 78 for the OT content, because that's the best bit, in my opinion. And yeah, thank you very much for your time. And I'll try and answer questions, but if not, add me on LinkedIn or something, or email me. Thank you very much.
All right. Thank you very much, Rick. This was a very, very interesting presentation. I did enjoy it, and it was, again, something else. There was one very interesting question, and there's a couple of questions, so maybe you can stay for 5 minutes after a presentation just to answer them. But there's one question I had in there, which I actually also had. How many times have you seen this kind of attack in the wild?
None. So to try and be as concise as possible, I didn't have kind of strategic level takeaways. But one of the things that I would say is that this is a long-term threat. This trying to even consider things like this is for an organization that is already very mature with their cybersecurity. If you aren't protecting or aren't confident about your protection against things like IT ransomware affecting your operational technology, that is the thing to be focusing on. And I'd actually say that focusing on your IT network and your architecture and your separation between IT and OT is the most important thing you should be focusing on before any OT security at all.
All right. Thank you very much for that answer. I do agree with that. Focus
Thank
on the
you.
basics, focus on that architecture and on the bottom. Definitely.
Absolutely.
Thanks a lot again for joining us in this QCTR and this event. You were the last speaker today. We went a couple of minutes over time, but I think it was very, very interesting to keep you there on stage. So thanks a lot, Ric. A lot of virtual claps to you and to all of the other speakers that we've seen today. We saw a lot of interesting topics on North Korean actors, Chinese actors, and of course, we had SQL injections. And then we also saw the dead man's attack on the OT environments. All right. Thank you very much. Just a couple of little notes. We do have 2 upcoming events. There's one about protecting yourself against DDoS on the 9th of September. And then in October, as always, the end of a quarter, we will have the next QCTR event for Q3 of 2025. We do call for proposals, so if you have an interesting presentation like we've seen today, interesting research that you want to present, feel free to drop your proposal through email to connect&share@ccb.belgium.be. We also have vacancies. Always at CCB, we're always looking for people, we're always expanding, we're always adding interesting people, engineers, and very, very smart people to help protect the Belgian cyberspace. And also, if you haven't been able to watch this whole thing, feel free to check all of our recordings and also this one, which will be available later on our YouTube channel, Cybersecurity Belgium. Thank you very much, and I hope you enjoy the rest of your day or morning or evening or night, depending on where you are. Thank you very much, and see you after the summer. Goodbye.